Here we'll be discussing exfiltration, a crucial process in water management. Exfiltration refers to the movement of water from an underground storage system directly into the surrounding ground. This method is commonly applied using systems like perforated pipes, which allow water to seep out along their length, or through underground vaults designed to facilitate water release. In this learning module, presented by BMPFast, our goal is for you to gain a comprehensive understanding of how exfiltration mechanisms operate and how to accurately calculate their effectiveness in removing pollutants. Remember, exfiltration is fundamentally considered a retention system, as it holds and then gradually releases water back into the environment. In this session, our learning objectives are to understand a key stormwater management practice, exfiltration. We'll define what exfiltration is, differentiating it from other infiltration methods, and explore why it's a popular best management practice, particularly in areas with limited ground space. We'll then demonstrate how to use the worksheets in the BMPFast software to calculate the annual removal effectiveness of exfiltration designs, emphasizing how these systems contribute to protecting our groundwater resources. Finally, we'll walk through a practical example project to illustrate the input information required to determine both the annual effectiveness and the total annual removal for specific exfiltration designs, whether they involve vaults or trenches with perforated pipes. We're now looking at two important subsurface stormwater management practices: the vault and the pipe exfiltration trench. An exfiltration trench is designed for subsurface storage and transport of runoff. Typically, it consists of a perforated pipe, which is then surrounded by natural rock or specialized pollution control media. When soil conditions and the water table allow, the stored runoff can gradually exfiltrate from the trench into the surrounding groundwater. The pipe itself serves a dual purpose. It significantly increases the overall storage capacity within the trench and promotes consistent exfiltration along the entire length of the system. In contrast, a stormwater vault is primarily an underground structure built to provide runoff storage, particularly common in urban environments where surface space is at a premium. A key distinction here is that while a vault stores runoff, it does not provide for the transport of that water in the same way a trench does. Both trenches and vaults can function as either detention or retention systems. When used for detention, they help manage peak discharge flow rates or attenuate the hydrograph, slowing down the release of water. As a retention system, they are designed to facilitate the exfiltration of stored water. For both detention and pollution control, these systems often incorporate specific pollution control media to assist in removing contaminants from the runoff. Ultimately, these types of best management practices are frequently chosen when there isn't sufficient space available on the surface for other stormwater management solutions. When we consider the annual effectiveness of exfiltration pipes and vaults as retention systems, a critical factor is their recovery rate. In situations with fast recovery, such as exfiltration and vaults located in high hydraulic conductivity limestone areas, the annual effectiveness significantly increases compared to systems with a slower 72-hour recovery period. For general runoff and recovery times up to 72 hours, we apply the removal efficiency tables published in the new 2024 rule. Specifically in Applicant's Handbook Volume 1, Appendix O, there are 80 such tables available. However, for fast recovery conditions, typically 3 hours or less, we then adjust the effectiveness using the provided graph. This adjustment can show an increase of up to 10% in effectiveness, though it's important to note that this increase becomes very small for large holding volumes or design treatment depths exceeding 2 inches. This concept builds upon foundational work by Evangelista in 1978 and Harper in 2007, who published results comparing the annual capture of runoff as a function of storage volume. The average annual effectiveness in high hydraulic conductivity rock layers, like limestone exfiltration areas, was calculated based on Evangelista's original work. The capture efficiency for fast recovery assumes that the full design treatment depth is available for the next runoff event because the water is fully exfiltrated within the 3-hour storm interval often used in Florida, also considering an initial abstraction of 0.1 inch. This adjustment for faster infiltration rates has even been incorporated into the BMPFast model. When utilizing the tables and graphs, you might find that interpolating for values other than curve number and directly connected impervious area in increments of 5 can be a bit challenging. When we talk about typical sections for trenches, we're generally referring to two common designs, each tailored for different exfiltration rates. The first type is designed for low exfiltration, meaning the trench is intended to remove the designed water volume within a period of 72 hours. The second common section is for high exfiltration, which is used when the trench needs to remove the designed runoff volume much more quickly, typically within just 3 hours. So the choice of section depends heavily on how rapidly water needs to be removed from the system. Here we're looking at an exfiltration pipe, which is an excellent example of an on-site retention best management practice, or BMP. The image on the left illustrates an exfiltration pipe construction that was implemented in an urban area 3 decades ago. It's quite remarkable that this system is still fully functional today, demonstrating the longevity and effectiveness of such designs when properly installed. Another similar application has been successfully used in a residential area, highlighting its versatility. You can also see a schematic accompanying the picture, which helps us understand the internal structure and how these pipes facilitate the infiltration of stormwater back into the ground. These images showcase the installation of exfiltration vaults, which are crucial on-site best management practices for managing stormwater. A key characteristic of these systems is that they typically do not use perforated pipes. You'll find a wide variety of exfiltration vaults available. Some are designed to store and exfiltrate very large volumes of water, while others are scaled for smaller areas or specific site constraints. Regardless of their type or size, all exfiltration vaults inherently provide a significant storage volume for water before it's gradually released back into the ground. We're looking at a real-world project example, drawn from a permit application, that will help us demonstrate the use of BMPFast in determining annual removal effectiveness. This project involves a proposed medical plaza in the Fort Lauderdale area, slated for an existing 2-acre general agricultural site. Due to the anticipated frequent traffic, this site is classified as high-intensity commercial. The owner's goal is to maximize the use of the land, and to achieve this, they plan to incorporate exfiltration vaults or pipes for stormwater management. This design connects the building's downspouts directly to the pavement, allowing stormwater to then flow into the exfiltration system. A critical site characteristic here, as identified in the geotechnical report, is the presence of highly permeable underground limestone rock. This high permeability means that we'll need specific percolation data from that geotech report to justify the stormwater removal rates, or alternatively we'll design for a 3-hour treatment volume. Regarding the hydrological parameters, the curve number for the non-directly connected impervious area is 80, and the directly connected impervious area is 1.0 acre. A significant performance standard for this project is that it must meet the impaired condition within an outstanding Florida water, or OFW, body. With this project description in mind, we can now proceed directly to BMPFast to enter this data and conduct the necessary analysis. Our next step involves entering the specific site and catchment information for our medical post-development site. An important consideration here is the performance standard. For any discharges into an outstanding Florida water or an impaired water body, we set the performance standard at the highest removal specification available, 95%. Regarding the site's environmental context, we note an annual rainfall of 64 inches, placing it within Zone 5. When we consider the watershed characteristics, both the necessary land use types and the event mean concentrations, or EMCs, are already incorporated into the BMPFast software, simplifying our data entry. It's crucial to remember that once all the catchment data has been entered, the performance percentage specified for this scenario will consistently be that highest level of 95%. When we utilize standard vault sizes for our system, we've found that the annual capture consistently exceeds 95%. Specifically, we're talking about a vault that measures 100 feet by 80 feet wide and 4 feet deep. These are standard dimensions offered by the manufacturer, and they come with a significant void space of 96%. This configuration allows for an annual treatment capture of 95.7%, which is excellent, as it successfully meets both our specified and net improvement standards. It's particularly effective given that the surrounding rock area can actually exfiltrate stored runoff water in less than 3 hours. In this specific scenario, the storage volume was greater than 4 inches, which, as expected, results in a very high removal rate. To obtain a summary printout of your results, you simply need to enter your configuration data into the system. Here, we're considering an option that involves using 1,220 feet of perforated pipe, with a 48-inch diameter, placed within an 8-by-5-foot trench. This particular setup would feature 4 parallel pipe trenches, each stretching 2,980 feet in length. These longer trenches would then be interconnected by 100-foot sections of trenched pipe, running perpendicular to the main parallel lines. With this configuration, the projected annual removal efficiency is also 95%. Groundwater protection is a crucial consideration, especially in areas with sensitive springs and estuaries. Sometimes the need is for additional water volume, and other times it's for cleaner water with reduced nutrient concentrations. While not a requirement for this specific project, in many other contexts, it's essential to determine the annual groundwater recharge volume and the average concentration of that recharge. To achieve effective groundwater recharge and estimate nutrient concentrations, absorption media is often selected. Stored runoff can exfiltrate through this media, which plays a vital role in calculating an average nutrient recharge concentration. This exfiltration process is typically quite slow, usually only about 5 inches per hour, meaning it often takes more than 3 hours to fully remove the designed runoff volume. When using structures like vaults, it's common to conduct a detailed groundwater discharge analysis. To calculate the recharge volume and average concentration, programs like BMPFast are available, which allow users to perform these analyses. Now we're going to add a specific sorption media, BNG24, to our vault within BMPFast to enhance treatment for exfiltration. Once you've added this media, you'll need to return to your exfiltration worksheet and hit the Calculate button. If you haven't already, please proceed to the configuration page and ensure exfiltration is selected as your best management practice. From there, you can continue to the summary page to view the updated results. With the BNG24 media in place, we observe an annual recharge of 1.602 million gallons per year. The average total nitrogen concentration, with the media, is now reduced to 0.6 milligrams per liter. For comparison, without this media, the average concentration would be equal to the event mean concentration, or EMC, which is 2.4 milligrams per liter. This demonstrates an average removal of approximately 75% for total nitrogen. You can also find the total phosphorus removal rates and concentrations detailed on the summary page. A key consideration for the owner involves the service life of the media within the exfiltration vault. There's a strong desire to avoid the significant disruption and cost of having to excavate the vault just to replace the media, with a goal of achieving a service life of more than 30 years. To determine if this is feasible, we utilize a specialized tool found in the Tools menu, specifically designed for exfiltration calculations. We input the vault's dimensions, a bottom area of 8,000 square feet with a 2-foot depth of media. This gives us a total media volume of 16,000 cubic feet. When these parameters are entered into the exfiltration service life tool, it projects an impressive service life of 50 years, which comfortably exceeds the owner's requirement. So what have we learned throughout this module? We began by understanding what makes up an exfiltration best management practice, or BMP. We defined exfiltration as the movement of water from an underground storage system directly into the surrounding ground. These systems can take the form of trenches with perforated pipes, which are designed to store and transport runoff, or they can be vaults specifically engineered for water storage. We then moved on to practical application, learning how to effectively use the worksheets within the BMPFast software. This included calculating the average annual pollutant removal and demonstrating how an exfiltration system can be leveraged to meet even the most stringent performance standards, like a 95% removal rate. A critical aspect we covered was protecting groundwater quality. We discussed how absorption media can be integrated into these systems to specifically remove nitrogen, thereby safeguarding our precious groundwater resources. We reinforced these concepts through an example project where we walked through the annual removal analysis for an exfiltration system. Finally, we covered the important step of saving your project data. Remember to always save your work, and your project files will have the BMPT file extension. This concludes our comprehensive look at exfiltration. To further enhance your knowledge, we encourage you to explore other learning modules, and then consider applying to take the competency test. Full details on this process can be found in the module specifically titled Self-Test. Thank you for watching this presentation.